properties to those of carbon was silicon. They therefore thought that silicon should be able in some way to build the compounds formed by carbon. However, all their efforts proved to be in vain. Because silicon had no ability to form a large number of compounds with other elements in the way that carbon does. The main reason for this is the strong bonds that carbon forms with its own atoms. The bond between two carbon atoms is very strong, for which reason it permits much longer and highly stable bonds. Although silicon is an element very close to carbon, it is unable to form such powerful bonds with its own atoms. The bond it establishes is weak and unsuited to the formation of long chains. In his book, The Chemical Elements and Their Compounds, the British chemist Neville Sedgwick describes how there is no alternative to carbon. We know enough now to be sure that the idea of a world in which silicon should take the place of carbon as the basis of life is impossible. The Earth is the only known planet to have the necessary conditions for carbon to form and give rise to compounds. For example, the temperature range needed for a carbon compound to be able to form is between -20 and +120 degrees Celsius. Carbon compounds start to freeze at -20 degrees and to fall apart at 120 degrees. We can witness this decay and this falling apart under world conditions. In a forest fire, for instance, the extreme heat entirely alters the structure of tree trunks. Carbon compounds undergo changes, which is the reason that the tree structure is radically altered. The carbon is now lost its original structure. As we have seen, carbon is impaired by temperature changes. If that change were to prevail across the world, life would disappear. This is one of the most important proofs that the Earth is specially created. The temperature range that permits carbon to give rise to organic compounds exists only on Earth. And this temperature range is a highly delicate one. To make a comparison, the temperature on Venus, the next planet to the Earth in the solar system, is around 450 degrees Celsius, and the temperature on Mars, the next planet after the Earth, is -53 degrees Celsius. It is impossible for carbon to give rise to organic compounds in such burning heat and freezing cold. It must also not be forgotten that the temperature in the stars measure millions of degrees, and that the temperature in the vasts of outer space is -273 degrees Celsius, or absolute zero. The fact that only the Earth possesses the specific temperature range necessary to support carbon-based life is a great blessing and a special creation. The important thing is to realize, by seeing these perfections, and by knowing Allah's matchless artistry, that one stands in need of Allah and should appreciate His greatness. Allah reveals this fact in the Quran. I seek refuge in Allah from the accursed Satan. Have you thought about what you cultivate? Is it you who make it germinate, or are we the germinator? If we wished, we could have made it broken stubble. You would then be left devoid of crops, distraught. We are ruined, in fact we are destitute. Have you thought about the water that you drink? Is it you who sent it down from the clouds, or are we the sender? If we wished, we could have made it bitter, so will you not give thanks? Have you thought about the fire that you light? Is it you who make the trees that fuel it grow, or are we the grower? When we examine carbon in detail, we see that not only the formation of this atom, but also its chemical properties have been specially determined. In nature, carbon is found in two separate forms, graphite and diamond. However, the compound it forms produce very different substances. All the very different organic structures, from the cell membrane to tree bark, from the lens of the eye to a deer's antlers, from the white of an egg to snake venom, all these consist of carbon-based compounds. Carbon combines with hydrogen, oxygen, and nitrogen atoms in very different geometrical forms and sequences, thus giving rise to very different substances. Some carbon compounds consist of only a very few atoms, while others contain thousands or even millions. Only carbon atoms can form such long and permanent compounds. In his book, Neville Sidgwick says this about carbon. Carbon is unique among the elements in the number and variety of the compounds which it can form. Over 250,000 have already been isolated and described, but this gives a very imperfect idea of its powers, since it is the basis of all forms of living matter. When carbon combines with other atoms to form organic compounds, the bond established between the atoms is known as a covalent bond. Covalent bonds are formed when two atoms share the same electrons. Electrons revolve in specific orbits around the atomic nucleus. There may be only 2 electrons in the orbit closest to the nucleus. The next orbit may contain 8, and one after that 18, and so on. The noteworthy point is that atoms have a predisposition to make up the number of electrons in their orbits. For example, oxygen with 6 electrons in its second orbit wants to add another 2 electrons, and thus complete the orbit with 8 electrons. No answer can be given to the question of why atoms have such a tendency, but were it not for that predisposition, life forms could obviously never come into being. Covalent bonds are formed thanks to the atoms' desire to complete their orbits. 2 different atoms that want to complete their orbits do so by sharing their electrons. The 2 hydrogen atoms and 1 oxygen atom that constitute water, for instance, build a covalent bond. The oxygen raises the number of electrons in its second orbit by sharing 1 electron with each of the hydrogen atoms. Each of the hydrogen atoms raise the number of electrons in its second orbit to 2 by using 1 of the oxygen electrons. Carbon thus gives rise to very different substances by building such covalent bonds. Methane is one of these substances. The formation of methane comes about by 4 hydrogen atoms building a covalent bond with a carbon atom. Since the atomic number of carbon is 2 less than that of oxygen, the carbon bonds with 4 hydrogen atoms instead of 2. As we said at the beginning, the bonds built by carbon constitute a very wide spectrum. The bonds that carbon establishes with hydrogen alone give rise to the large family known as hydrocarbons. This family includes natural gas, liquid petrol, fuel oil, kerosene, and various machine oils. The hydrocarbons, ethylene and propylene, are the basis of the petrochemical industry. Other hydrocarbons give rise to such compounds as benzene, toluene, and turpentine. The mothballs we put in cupboards to protect our clothes against moths contain another form of hydrocarbon. Hydrocarbons that combine with chlorine or fluorine produce such different substances as anesthetics, fire extinguishers, and the freon used in refrigerators. The covalent bonds that carbon builds with hydrogen and oxygen represent another wide spectrum, including alcohols such as ethanol and propanol, as well as aldehydes, ketones, and fatty acids. Two important substances formed by carbon, hydrogen, and oxygen compounds are the glucose and fructose in the foods we eat that provide us with energy. Cellulose, the constituent of the hard part of trees that represents the raw material for paper, beeswax, vinegar, and formic acid, again form as the result of the covalent bonds that carbon constructs with hydrogen and oxygen. When carbon builds bonds with hydrogen, oxygen, and nitrogen atoms, very important compounds once again result. The most important of these are amino acids, which form proteins, our body's building blocks. The nucleotides that make up DNA are also molecules made up of carbon, hydrogen, oxygen, and nitrogen. In short, the covalent bonds constructed by the carbon atom are among the most essential preconditions necessary for life. If carbon were unable to build covalent bonds with oxygen, nitrogen, and hydrogen, then life could not exist. What enables carbon to form these bonds stems from a characteristic chemists refer to as metastability. The well-known biochemist John Burden Sanderson Haldane describes this feature as follows. A metastable molecule means one that can liberate free energy by a transformation, but is stable enough to last a long time unless it is activated by heat, radiation, or union with a catalyst. This technical definition means that the carbon atom has a very unique structure, thanks to which carbon is easily able to form covalent bonds under normal conditions. However, there is one very interesting point here. Carbon's metastability, which is essential for life, only applies within a very narrow temperature range. Above 100 degrees Celsius, carbon compounds become highly unstable. We all observe this in our daily lives. An example of this is when we cook a piece of meat. Cooking it is actually changing the structure of the carbon compounds. One important point needs to be emphasized. The meat that is being cooked now becomes entirely dead. In other words, it assumes a completely different structure to that in a living organism. Most carbon compounds decay at above 100 degrees Celsius. Many vitamins break down at once. Sugars undergo structural change in the same way and lose